this one is reflecting astronomical telescopes. The objective now, of course, we are saying that, remember we have telescopes, we have optical instruments. We first looked at the eye, okay, but of course, you know, these are instruments which help eye in seeing. So we have microscopes and telescopes, and then we have others like projector, lantana, we have the camera. Now we are looking at, we looked at microscopes, then also telescopes. Telescopes we have refracting and reflecting. So now we are looking at reflecting what? Telescopes. Deflecting astronomical telescopes. The objective this time is a concave mirror of long focal length because it focuses a distant object. Then there are three types. One is Newtonian, Coude, Cassegrain. So we are starting with the Cassegrain now. Starting with the Cassegrain deflector telescope. So we have, it uses a concave mirror, okay, a parabolic mirror, a concave mirror of long focal length, and then a convex mirror. This is a convex mirror. So now the rays from the distant object, these are the rays from the distant object, are first reflected at the concave mirror and then at the convex mirror to form a real image I, which is situated at the pole of the concave mirror. This image is such a way that it coincides with the principal focus of the eyepiece, and then eyepiece forms a fine image which is virtually magnified to infinity. So the final image is formed at what? Infinity. So the objective consists of a concave mirror of long focal length. Parallel rays from distant object are first reflected at the concave mirror. So that means that these rays which are reflected from the concave mirror forms an image I prime. So this image formed by concave mirror acts as an object for the convex mirror. The convex mirror forms a image at the pole, and then this eyepiece is adjusted such that this point coincides with the principal focus of the eyepiece, and then eyepiece forms the final image at infinity, which is magnified and virtual. So this is Newtonian deflecting telescope. Here we are going to use an objective concave mirror of long focal length and a small plane mirror which is slanting. Rays from distant object, parallel rays of light from a distant object are first reflected at the objective and then at a smaller slanting plane mirror to form a red image I. The plane mirror helps to bring the intermediate image to a more convenient focus, which is this, to a more convenient focus. Then this plane mirror is small so that the effective focal length of the objective is not tampered with, is not affected. Is not what? Is not affected. Then after that we say, thus the eyepiece is adjusted so that the final magnified virtual image is formed at infinity. So when they ask you to describe the operation of a reflecting telescope, you use one of the three. There are three. So here they do not specify. In most cases, they do not specify. Now, if they don't specify, also when you are describing, don't tell us which type you are describing, because you may tell us it is a Newtonian, yet you are describing a Segway. So do not commit yourself to the type. You just pick out any at random that you can explain to you are more convenient. Okay. The one who can easily explain with ease, without panicking, explain that. So this is the last one, which is Coude refractor telescope, and we have for it uses an objective concave mirror of long focal length, the convex mirror, and a small plane mirror which is very small. This is eyepiece. So I said that an objective consists of a concave mirror of long focal length. Parallels from distant object are first reflected at the objective, and then to the plane, then to the convex mirror, which then reflects it onto a scientific small plane mirror to form a real image eye. The eyepiece is set such that the image eye coincides with its principal focus, thus forming the final image at infinity, which is magnified and real. The eyepiece is set such that eye coincides with its principal focus, thus forming the final virtual and magnified image at infinity. Of course, we know that an object which is pressed at the principal focus of the lens, the image is formed at infinity. That's the reason why we are saying that this eyepiece is adjusted such a way, or is set in such a way, the image to coincide with its principal focus. If the image coincides with its principal focus, then this eyepiece is going to set or to form the final image at infinity, which is magnified and real. You understand? Next. We can also advantages of reflecting telescope over refracting telescope. Advantages of reflecting telescope over refracting telescope. Number one, there is no chromatic aberration. There is no chromatic aberration since refraction does not occur at the objective, which is mirror. Of course, you know that chromatic aberration occurs in lenses. When the white light is split into different colors, such that at the principal axis, different colors are brought to different points along the principal axis, leading to formation of colored images when they overlap. So here, since the objective is a concave mirror of longer focal length and of small aperture, we shall now say there is no chromatic aberration. That's number one. Number two, spherical aberration can be minimized by using parabolic mirror. Spherical aberration can be minimized by using a parabolic mirror as the objective. Of course, you know, spherical aberration occurs both in spherical mirrors and lenses. And when a wide beam of light is incident such that marginal rays are reflected and converge at a point near the pole, and then the paraxial rays converge at a point far away from the pole, resulting in the formation of bloody images. So here, since we are using a parabolic mirror, there is no spherical aberration. Next, it is much cheaper and easier to make a mirror than a lens, since only one surface requires to be grounded. Only one surface is grounded, but for the case of the lens, two surfaces. Images are brighter because it is easier to make mirrors of large aperture, which collect a lot of light, compared to making a lens with large aperture. Next, resolving power is greater, i.e., seeing different images as separate. Then we look at disadvantages. Disadvantages, they tarnish easily and absorb light, resulting in dull images. Or alternatively, we can say the silvered surface wears off with time. That's number one. Number two, there is loss of energy at the point of incidence. Differences between telescopes and microscopes. Differences between telescopes and microscopes. What are the differences between telescopes and microscopes? So we draw a table. We shall say between and microscopes. So we shall draw a table. Here we shall put microscopes. Here we shall put what in telescopes. So the first one we say, number one, say use it to view a near object. Use it to view a near object. This one used to view a distant object. Used to view a distant object under a telescope. Then shall say under a microscope, objective lens has a small focal length. Objective lens has a small focal length. Under telescope, we say objective lens has a longer focal length. Then we say larger resolving power in microscope. Microscope has larger resolving power, has smaller resolving power. Has smaller resolving power. There is in normal adjustment. In normal adjustment, the final image is formed at the near point. Then under our telescopes, in normal adjustment, the final image is formed at the infinity. So the asking questions like define the visual angle, explain why farthest vertical pole in line with the others of equal height looks shorter, define the term angular magnification, etc. Let us go and look at projector lantern. So this is the projector lantern. So the projector lantern, we say it is designed to form a magnified image of the slide on the screen. It's designed to form a real image of the slide on the screen. So this is, it consists of concave mirror, then condenser, the slide, the projection lens, and then the screen. So I say that as long as source of light is placed at the center of curvature of the concave mirror, then next, the light from the source is reflected back. Since it is placed at the source at the center of curvature, light from the source will be reflected back, okay, along its own path, and it is concentrated, reflected back into the condenser, which concentrates it onto the slide. So the condenser concentrates light through the slide. The projection lens forms a magnified real image on the slide. The projection lens forms a magnified real image of the slide on the screen. Then uses functions of the parts. Functions of the parts. What are the functions of the parts? We start with the number one. Number one, we start with the concave reflector. The concave reflector concentrates light from the source to the condenser. So as we've already seen that this one concentrates light from the source to the condenser, this concave mirror. Then next, the condenser uniformly illuminates the object or the slide with light from the source, or alternatively, or the condenser concentrates light towards the slide. Next, number three, the slide bears the object to be projected to the screen. The slide bears the object to be projected to the screen. Projection lens focuses and magnifies an upright image on the screen. Then lastly, screen is where the image is formed. So those are the functions of the parts. Then you can go and look at NB. A projector is used for showing a magnified image of the film or slides on the screen. Number two, the film is the region where the slide is to be placed. Number three, the magnification of the slide is given by M equals V over U, is given by m equals v over u, or m is equal to v over f minus 1, where v is the distance of the screen from the lens, u is the distance of the slide from the lens, f is the focal length of the lens. Then we can say for any enlarged image, linear scale factor squared, linear scale factor squared is equal to image area divided by object what? The slide is in the form of a rectangle. Is in the form of what? A rectangle. So we shall now say linear scale factor, linear scale factor is equal to square root of magnification. Is equal to square root of magnification. Actually, this is the linear scale factor. So that means, squared here. So here we take square root. We shall now say linear magnification is equal to linear magnification is equal to that's is equal to square root of image area divided by object area. So in this case, this linear scale factor is equal to this, okay? So when you put it there, here it will become magnification squared is equal to that, then take it square root. So we shall use those equations and look at one example. Okay? So this is what we have. A projector produces an image area on this to the screen. So that means that you have this is a lens, this is a lens, this is a slide, okay? This is a slide object here. Then this is the image. So this is the object, this is the image, the distance, this is u, and this is v verti, this is v. So this is the lens. So they're asking us find the focal length. So we shall now say that magnification is equal to square root of image area divided by object what? Area. But in terms of focal length, we shall have v over f minus 1. So we substitute. This is image is 1.2 square root of 1.2 times 1.8 divided by this one in meters. This is 0. We can say it is 0.024 times meters is 0.036 under square root. It will give us v over f. Our v is 5 meters divided by f minus 1. Using a calculator, our f will now becomes 0.098 meters, or f becomes 9.8 centimeters. Then another distance of the slide from the lens. So we can now say magnification is equal to v out of u. So our u, if you want, can first get that one. Or 1 over f equals 1 over u plus 1 over v. So 1 over 0.098 is equal to 1 over u plus 1 over v, which v is 5 meters. So U will now become, using a calculator, you can obtain your U as 0.1 meters. 0.1 meters. Is that okay? Then let us go and look at lens camera. The lens camera, and we say lens camera or photographic camera. We write a subheading and we say the lens camera. The lens what? The lens camera. Stroke photographic camera. Photographic what? Camera. We say this is that a camera consists of a lens system, a light sensitive film at the back, and focusing adjustment, and focusing arrangement. The latter is used, that's LATTER. The latter is used to adjust the distance of the lens for proper focusing. That's the shutter. The shutter is used to adjust the distance of the lens for proper adjusting. Let us see the diagram. So this is the diagram. And this one is extracted from Lancaster, Advanced Physics by Lancaster. Okay, so from that diagram, and then we are going to say camera lens system. So we are going to look at how it works. Camera lens system refracts light from an object onto the screen. Next, the film is coated with a light-sensitive substance and is where the image is formed. Next, the shutter cuts off light where necessary, thus controlling exposure time. The stopper or diaphragm regulates amount of light reaching the film. The diaphragm adjusts the size of aperture, which is an opening which light passes to reach the retina. Focusing ring focuses the image on the film. So now that is how we look at the use of this one diaphragm. This one is to control the size of aperture, which regulates amount of light entering the film. Then this shutter controls the time of exposure for which the film is exposed to light, and then it closes. Then the lens is to focus and form the image on the film. Then this adjusting ring is to adjust the diaphragm or the size of aperture. The film, then said film. Lastly, the film is coated with light sensitive material or substance, and this is where the image is formed. And B, chromatic aberration in the photographic camera is minimized by use of chromatic combination of two lenses, one convex and the other concave, to form a chromatic doublet. To form a chromatic doublet or doublet. Doublet like this. Doublet. To form chromatic doublet. That's what we call chromatic doublet. Spherical aberration in a photographic camera is minimized by use of diaphragm, which cuts off marginal rays and only allows central rays to pass through. Now you can make research about the human eye. The next one is the human eye. The human eye. Now, the human eye has the following parts: converging lens, which focuses image onto the retina; iris controls amount of light entering the eye by controlling the size of the pupil. Number 3, pupil is a circular opening through which light enters the eye. Retina this is the light sensitive part where image is formed. Similarities between eye and camera. Similarities, of course, we know both have converging lens. Both have light sensitive parts for image formation. Of course, one has retina, another one has film. Both have openings that allows light. Both have ability to control amount of light entering. Differences between the eye and camera. Then we see eye is biological, while camera is artificial. Next, the eye lens has the fixed focal length. The eye lens has a variable focal length, while the lens in a camera has a fixed focal length. Then next we go to accommodation. What is accommodation? Accommodation is the ability of the eye to focus an image of an object by altering the focal length of the lens. So they will ask you to define accommodation. It is the ability of eye to focus the image of an object by changing the focal length of the eye lens. The near point is the closest point. Near point is the closest point at which the eye can focus clearly. Far point is the farthest point at which the eye can focus clearly. For normal eye, the near point is 25 centimeters and the far point is at infinity. Let us look at eye defects and their correction. The first one we shall look at: eye defects are caused by inability of accommodation. So the first eye defect we look at: long-sightedness or hypermetropia. A long-sighted person sees only far objects clearly because their images are formed on the retina. Because their images are formed behind the retina. A person with long-sighted sight defect can see near objects clearly, and this occurs when the image is formed beyond the retina. The person with long-sighted sight defect cannot see near objects, Cannot see near objects because the image are formed behind what? Retina. Now, in fact, the person who, a long-sighted person is the person who can see far objects clearly because their images are formed on retina. In other words, a long-sighted person, this is a person who cannot see nearby objects because the images are formed behind retina. Then we can say this happens when the eyeball is too short. The eyeball is too short and all the images are focused behind retina. Correction. It is corrected by using a suitable converging lens called converging meniscus. Try to look for those diagrams, please. Make research also. Is it okay? Then we got short-sightedness or myopia. A short-sighted person sees only near objects clearly because they are formed on retina. A person with short sight defect cannot see far objects clearly because the image is formed before retina. This is due to the eyeball being too long. Eyeball is too long. Correction. It is corrected by using a suitable diverging lens called diverging meniscus. So here they are saying that a person in a person with normal near point at distance 25. So this is the eye of the person, this is the eye. It's correcting using the diverging lens. Using the diverging what? The diverging lens. So we put here the diverging meniscus. We say that this person who uses that, this is short-sightedness, meaning that this person cannot see the far objects clearly. So that means that this person can see the near object clearly. So let me say now the object is here. So this one does divergence like this. So it appears to come here. Like this. So, but the man were coming from somewhere here. This is object O. So this object appears to be at I. So that means that remember from here, that means that if the object appears to be I, our V will be negative 25. Because it's a virtual image, the virtual image, then our F will become what? So this is 20 what? This is 25. Our F is negative 200 what? Centers. So I should say 1 over F equals 1 over U plus 1 over V. 1 over negative 200 is equal to 1 over U plus 1 over negative 225. So 1 over U will become 1 over negative 200 plus 1 over 25. So our U becomes 28.6. 28.6 centers. Then they can ask you what is meant by normal adjustment as applied to microscope. Define the term angular magnification. Describe with aid of a red diagram the action of magnifying glass in normal adjustment. Hence derive its magnifying power in terms of focal length. Next, describe with the aid of a diagram the action of magnifying glass in forming the final image at infinity. Hence, show that magnifying power m equals d over f. So those are some of the questions they can ask. Explain the term eye ring as upright telescope, they give you 2 marks. Explain the significance of eye ring, they give you 2 marks. So should give us the 2 points that eye ring is the best position where an object should be placed in order to receive all the light entering the instrument. Then we say that you go ahead and say at this point the image seen is brightest or is brighter. And also go ahead and tell us that this is actually the image of the objective that the eyepiece forms. Yeah. And many others. So that marks as the end of light. So that's a section of light, which is section A. However, of course, for consultations, my number 0785 132 106 or 0705 786 202 for consultations and coachings. So we carry out online coaching using Google Class, numerical class. We do that. So yeah, you can always get back to me in that inbox of mine. Yeah, and then please always make sure, try when you get an opportunity, be part of us in the class. Let us engage ourselves, and we shall find this physics very simple. And trust me, if you become serious, you will score. And the A's in physics are not so hard to score. However, it takes someone who's courage to go an extra mile so that you score that A in physics. Otherwise, it may not be simple for you as you may think if you don't go an extra mile. Other than that, let me stop at that. So that's the end of the section.